Let me see. You should be able to see the recording now. I just released it, so I need to change the camera. I don't need the tracking camera. Yeah. Hey, good evening, everyone online. I hope you guys stay warm. The temperature here is dropping. Hello, can you guys hear me? Okay, great. So I remember last time we stopped at the naive Bayesian network, Bayesian belief networks. Okay, right? So last time we stopped here, right? We didn't go through the support vector machines, right? Or we have gone through it. Yeah, it's been 2 weeks, so I lost my memory. Yeah, I remember last time I stopped at this example. I remember I introduced the kind of fraud in the inference. I remember one student pointed out, and this time I would like to offer you a good one. Okay, last time was trying to see like how many of you know it. Yeah, remember in the implementation of Bayesian belief network, there's one important cadence here. A node in a Bayesian network is conditionally independent of all of its non-descendants if its parents are known. Okay, non-descendants. What is the non-descendants? So wait. Huh? Oh, sorry. Forgot. Huh? See? Does it work? Okay, so I'm turning on the projectors for our classmates sitting in the classroom. I forgot that. Let me write out something first. Hmm? Why it does not project? Let me see. Share screen. Other ones options. Let me see. Mhm. No source. Yeah, we are good now. Okay. So basically, we want to compute which will be equal to D conditional HD and multiply PhD and divide by probability of E D C P B P, right? Solution space. Hmm? So it should be PED conditional HD multiply PCP conditional HD and PBP conditional HD multiply PhD. Divided by PED PCP PBP. And it's equal to HD condition on ED and PCP condition on HD proportion and PBP condition on HD. Right? Then we will use this proportion to compute these two values, then do the comparison. Okay, next, let's go into the today's concept, support vector machine. We will first talk about using support vector machines to do the classification. Basically, we want to using support vector machine as an algorithm. If we look at the data distributed in this two-dimensional space, and these all data points, they are labeled as two classes. One is a green square, another is a circle. So what we want to do is we want to find out a decision boundary to separate data to two parts based on learning the data relationship. Okay, and this decision boundary is called hyperplan in support vector machine. So there are many decision boundaries we can use based on this example. For example, we can use this one. Note there's B1, that means decision boundary 1. We can use another one, B2. Either of them can separate data well into two classes. That means based on either of them, all the data with circle, they're on one side, and all the data with green square on the other side. Okay. The problem is that in a space of data distributed in this two-dimensional space, we can find many such kind of decision boundaries. But we want to find one better among them. Then how can we define that which boundary is better among those data points? So people propose that we need to find out a boundary, decision boundary or hyperplan, which can maximizes the margin between two sets of data points. Okay. So what is the margin? The margin is that given a decision boundary, then you move the decision boundary with one direction, then it touches, first touching the data points, then you move the decision boundary towards another direction and it first touches data points. Then that margin indicates the margin of the decision boundary, and we want to maximize such kind of margin. And then data points located at the margin the edge of the margin of the decision boundary, they are called support vectors because they are the data points that the algorithm will find out to support them, the algorithm to decide what the decision boundary should look like. So B1 is naturally considered than B2 because we think we try to maximize the margin. So that means the decision boundary best differentiate these two types of data points in terms of the classification. So some simple math for support vector machines. So you can see that the B1, we can write it as a linear form, okay? And we set two margins with a positive one and negative one label. Then based on integrating these three, we will have a stepwise decision. That means if any of the Wx plus B larger than 1, okay, and we find out data in this space, those data will be assigned with label 1. And any data points less than equal to -1, okay, then we will assign it to a -1. So two classes. Okay, we talk about a simple two-class classification problem with a linearly separable case. Okay. Then based on this formulation, the margin actually can be equal to 2 over the vector norm of this W. So you don't need to care about how to get it, but you just need to remember it. Okay. Then this case is actually a linear support vector machine with such kind of decision rules. And with such kind of formulation, what we should learn about the SVM model from the data. That is the W, the weights, and the bias. Okay. So we want to determine the weight and bias so that the margin can be maximized. You can see the margin is here. We want to maximize the margin based on this value. Then learning a linear support vector machine can be equivalent to maximize this margin. And such kind of maximization problem can be equivalently reinterpreted as a minimization problem by reverse the position of these two guys, okay? So if we want to maximize such kind of margin, we want the bottom one needs to be small enough, then it will be minimize the top one, okay, in this kind of term. And such kind of objective needs to be optimized with subject to considering the following constraints, okay? And such kind of constraint optimization problem we solve using Lagrange multiplier methods. So yeah, so we can try to add a little bit math here to demonstrate the how the linear SVM gets solved analytically. Okay, you guys don't need to remember or just kind of broaden your knowledge. You know it, then you can know it. If you don't know it, it does not matter. All right, so based on this guy, we can know that the problem, optimization problem, is minimize with considering the W and B. That's the two parameters we need to learn for the SVM. Okay. And the objective is 1/2 the vector W multiply the vector W. Okay. Or we can write it this way. This dot product. And we actually integrate or synergize this two-stepwise constraint with this one by multiply yi into this term. Okay. So, you know, yi has binary values. Okay. If it is +1, then multiply this one, then the over term will still be larger than or equal to +1. If yi equal to -1, then you multiply this term, it will become such kind of form. Okay. So we will have a unified constraint plus b yj larger than or equal to 1 for all y. For all j, sorry. Then you said like this constraint optimization problem can be solved with a Lagrangian multiplier. Then how this Lagrangian works? So this is the basic problem formulation. Then we can actually move the constraint back to the objective function by applying a Lagrangian multiplier, which is alpha. Okay. Then we will have another equivalent form of the problem. The loss function, consider the weight and the alpha, which is equal to 1/2 weight multiply weight minus the summation of alpha j multiply wx plus b multiply yj minus 1. And this summation consider all the j. Okay. Then this alpha is a kind of Lagrangian multiply. So we call this form the prior problem. If you have knowledge about the optimization, then you know that the prior problem will be transformed to a dual problem equivalently with a process. This is called duality. Due to the duality of the problem, the prime problem can be converted to a dual problem. So the dual problem I made a mistake. This is not prime. I didn't write out the prime problem. Okay. So this is just the convert the original problem but multiply the Lagrangian multiplier alpha. So the constraint is all the alpha j should be positive, larger than or equal to 0 for all j. Okay. So our goal is now to solve a min-max problem. So minimization is the same as the previous one. We want to minimize the objective with consideration of W and B, but we want to do a maximization. with consider all the alpha. Then the loss is written as this, okay? Then the primal problem will be, can I just clean it and start other writing? And based on the previous setup, we can write the primal problem as min max WB and alpha 1/2. This is the margin, okay? It's like this. And minus the penalty, which is the constraint multiplier Lagrangian multiplier. Okay, so this is the penalty. So such kind of problem can be transformed to its dual form. So the dual form will be switching. Based on transforming to a dual form, we can switch the max min order. It's 1/2 square minus the summation of the alpha multiply Wx plus b multiply y minus 1. Okay. J for all the j. Okay. So this is this can be mathematical proof that the two problems are equivalent based on the Slater's condition in the convex optimization. Okay. So this is not always equivalent, but in this case is. Okay. And we can solve this problem by solving such kind of optimization problem. We first fix alpha as a parameter and take derivative of this loss function with respect to W and B. So it will be take a derivative according to W. Then what do we have? So these two move to the front and they're canceled. So we have the first term W. And how about here? It will be summation. It's kind of linear term, okay? So it will be alpha multiply y multiply x, alpha j multiply yj multiply xj for all the j. Because b here is treated as a constant, it is not related to w, so this term disappear and last term disappear. Okay, so here this w becomes 1 by taking a derivative. Can I type? Because there are so many stuff here, it's not easy to do the typing. I try to write well. Okay. Can move this a little bit, yeah. And we also take derivative of the loss function L with considering B with respect to B, okay? And look here, the first term is not involving B, so it is 0. And the second term involves one linear B, okay? So it's just summation. Negative sign you cannot forget. And alpha multiply B multiply Y, okay? So it's just alpha. Sorry. Yeah. Huh? This is alpha J multiply Yj. And for all the J, okay? So we have the first solve this optimization problem with fixing alpha as the parameter. Then we focus on the minimization. Okay. Then after taking derivative, what should we do? Yeah, set it to 0. Then W, by setting this one to 0, then W has a term as this. Okay. So another is just this term equal to 0, but it's not involving any B. So next, what we can do is we substituting W and B with the term that we obtained, then we do the maximization, okay? So actually it becomes, by substituting the W, basically the W form, then the problem will be converted to a maximization problem involving two types of variables. One is alpha, another is the summation of alpha Y equal to 0. Okay. Then the term will be summation of alpha J for all the J minus 1/2 summation Yi Yj for all the Ij alpha I alpha J. Okay. Xi dot product Xi. And this will be the maximization problem. Then we can solve for alpha, next solve alpha directly. Okay. So the calculation of B can be done once the alpha is solved. Okay. So B will be equal to Y minus W multiply X. Okay. based on this original formula. So that's only applicable to the support vector machine, linear support vector machine, with the simplest case that two types of data, they are separable. The separable case means here, the two data can be separable. But in reality, this ideal scenario is very difficult to meet. A lot of times, we are facing a problem like this. Data have very complicated relationships, and they probably are not separable in reality. We cannot find an ideal decision boundary for separating those two data sets, two types of data, two classes of data. So go back a little bit and finish one more slide in the linear separable SVM. So based on that, we will know W is equal to the optimization of the W will be equal to the summation of alpha multiply Y multiply X. Okay. And B is equal to Y minus WX. Okay. So that means the decision boundary, they are actually mathematically also can be seen that they are depending on just depending on a number of data points, okay, sitting on this border. So those data points are called support vectors. And this is why this algorithm called support vector machine, because this is the machine to finding support vectors to offer decision boundary, okay? Then once we have W and B determined and given a test record, how can we using SVM to do a classification? You basically just feed the data into these linear boundary, and you check whether it is larger than equal to 1 or less than equal to -1. So if it is larger than equal to +1, then the data will be assigned with the class +1. And it is less than equal to -1, then this data will be assigned with the class -1. So what if the problem is not linearly separable? How do we deal with it if the data are not linearly separable? Any ideas? There's no ideal solution because they're not linearly separable. They're actually not separable. Finding any decision boundaries, you will always have some data points mixed. Okay, you cannot find any. Okay, you cannot find a feasible decision boundary can ideally separate data of two classes into each of their side. Then what can we do? We do one step back. We introduce a new variable, which is called slack variable, epsilon. And the purpose of this slack variable is to allow us to offer some tolerations. Then the problem becomes a little bit complicated, is we want to introduce a slack variable, allow us to find an optimal decision boundary, but tolerate a little bit with their violation, okay? So how can we calculate the violation? We add their distance, okay, together. And we want to minimize such kind of violation. Then we revise our constraints by introducing this slack variable. That means we want to classify one data points to +1. We allowed it to we don't strictly require it to be just larger than equal to 1. We allow some tolerance. That means if it is not strictly larger than equal to 1, it is a little bit lower, okay, fitting these slack variable requirements, then we tolerate with it. We're okay with it, okay? So by introducing this slack variable, then we want to minimize our toleration. The optimization means indicates that we want to minimize such kind of toleration. Then we introduce a very important learning variable, C. So when you implementing your SVM algorithms, no matter in R, in Python, in MATLAB, this variable C needs to be well tuned. Okay, a well tuning of this C controls the minimization of this slack variable. So there's a trade-off. You want to tolerate more, or you want to find out a more strict decision boundary. So this one is to find out a decision boundary to maximize the margin, but this one is to optimize the tolerance. So there's a trade-off. Okay. So this is the first important variable needs to be tuned in fitting a support vector machine algorithm. So basically nothing is changed, but indicating such kind of slack variable. So the loss of learning SVM will be a little bit changed by adding this term. But in general, the objective function is similar, but with different constraints in this case. So the next scenario is more challenging. Based on this figure, we can see that the data is separable, but we need to apply a nonlinear decision boundary. Here is a circle, okay? Nonlinear decision boundary. And based on our vision examination, we will find out this decision boundary can be written as this. Then how can we convert the SVM algorithm or extend SVM algorithm to handle such kind of scenario, to handle such kind of nonlinear support vector, nonlinear decision boundary? So the trick is called transform data into a higher dimension space, but more academically, people would like to prefer say we apply a kernel. So that's the second important concept in SVM. When you apply SVM, you need to tune your algorithm by choosing different kernels. And here is the reason. The kernel is transforming the raw value of the data to another space. In this example, we want to see that the original space is like this, but by applying a kernel, projecting here is a more specific description. By such kind of transforming, the data becomes linearly separable. Okay, linearly separable. So this is the magic of a kernel function. Then what is the difference in math is or the original xi will becomes a kernel function of this xi. So that means this linear fit part will be done based on the transformed value of x. Okay, got it? Got the main idea is okay, you don't need to touch the behind mathematical proof, but this is the main idea. So the loss function will become, has a similar structure, but some changes, okay, here. Basically the x will be fed into a kernel to change its value. Then we fit in a linear SVM. Then you may ask a question. Hello, professor. So how can we optimize the kernel function? Because we have a data coming in, we don't know if the data is complicated, for example, a higher dimension, not just two, then we even cannot visualize and we don't know how the data pattern looks like. Then how can we optimize the kernel choices? How can we determine which kernel is the optimal to the data I have? So the response is the kernel cannot be optimized. The selection of kernel cannot be optimized. But you can always select the more appropriate one by trying. So this is also called parameter tuning, tuning hyperparameters. Here, the kernel is one of the hyperparameters. Basically, in implementing SVM, you will always try a set of classical kernels. And in each of the SVM package you use in Python or R, they default carry some options of kernel functions that you can choose. Some popular ones like polynomial kernel, okay, Gaussian kernel, and like RBF and others, okay? So if you want to try a very weird kernel that's rarely discussed, and you have to program from beginning by yourself. You cannot just call the package in Python and R if they don't have that kernel. Okay. So determining an appropriate kernel is just doable via trying, or in Mandarin it's called 调仓. Okay. So that's why we called some of the data scientists 调仓侠. That's here. So you call the package, then you need to explore the optimal configurations of the SVM hyperparameter setup. So I basically address the questions in the next slides. What type of mapping function or what type of kernel should be used? It is determined based on your trying. Okay. And how to do the computation in high dimensional space. So most computation involve in the dot product of the kernel. And curse of dimensionality, you need to determine the best dimension to control the dimensional space. Okay, so this is the kernel trick. Here is some of the kernel functions: polynomial, Gaussian, and hypertangent for SVM. So the advantages of using kernel. So you don't have to know the mapping function, okay, for the data. And computing dot products in the original space avoids curse of dimensionality. But not all functions can be kernels. So you must make sure that there's a corresponding kernel in some high dimensional space. Okay, or you can check Mercer's theorem. That is a little bit theoretical part. You can refer to the textbook if you have interest on exploring the theory of SVM. All right, so we finish the SVM part, and next we will wrap up the contents of classification from a general way. We will talk about the classification errors and some of the addressing some of the overfitting issues and so kind of. So let's take a break and let's come back at 8:10. Okay. All right, let's come back. So we talk about different classification models. Then to evaluate which model works better, we will look into the error performance of each of the classification model. Basically, we will look into 3 types of errors, or usually we focus on 2 types of them. The training and testing. Okay, so most of the time we look the first two, but sometimes we also look into the generalization error. Then we will go through like what does those error mean in classification. So training error, that is the apparent error, which is the errors committed on the training set. That means based on using the training data, then the error of your classification model developed based on the training data. The test error is a little bit different. The test error is once your training model is fixed, then we will directly apply it into the test data set. Then you get a test error. And the generalization error is a kind of expected error of a model of some random select of records from the same distribution. That means you would like to test whether your model is still generalizable. Then you find out, and this is usually done with simulation. Otherwise, in the real world, you cannot measure, you cannot make sure that the data comes from the same distribution. But in simulation, you can use the same distribution to further generate some of the data to do such kind of computation of the generalization error. Okay, so this is usually sometimes we say, okay, based on the data we have, after examining, we find out our data follows some certain kind of distribution. Then we develop a model based on such kind of data. Then we get the error. Then we would like to say such kind of model can be continuously utilized in the data with the same distribution, and its performance will be kept. So the error trend during the training of the decision tree or growing of the decision tree. So this figure shows that we grow a decision tree model. So the decision tree we have talked 3 weeks ago. So hope you guys still remember. It's kind of like this. Okay. So the number of nodes, we count the number of nodes, okay? So when you grow a tree, the number of nodes starts from 0, and you can continuously grow the tree with increasing the number of nodes. And most of the time you will find out the increase of the node will help with the significantly decrease of the error. That means the model becomes nicer. The error drops, that means the model becomes more accurate. But such kind of sharp drop usually happens at the beginning stage, that the first number of nodes. And after a certain number of nodes, you are going to make the tree specific. And adding more nodes has less effect on decreasing the error. Okay. So here, this place, if we cut it here, that means a decision tree with 4 nodes. And the decision boundary is like this. We have 4 decision boundary. 1, 2, 3, 4. Okay. We have 4 decision boundary. But if we do a cutout here, that means we grow the tree and stop here. And that will be a decision tree with 50 nodes. And the decision boundary will be this complicated. Okay. And you will find out the further structure of the tree, they're actually making decisions in some places, have dense data, but less of interest in our classification performance. And which tree is better, a small tree or a more complicated tree? to determine which tree is better, then we have to use two types of errors, training error and test error. So if we have a tree after growing the number of nodes have such kind of results, the training error close to the test error, and this tree model is, we say it is with a high quality. That means its performance is consistent. And here, the maximal is the number of nodes of 9. Okay. So we can see that we grow the tree with maximally number of nodes to 9. It can kept a good performance in our example. But if we keep on growing to like 150 after 9, wow, the training and test error starts to split. They become to have a very large gap. And this phenomenon, we usually say is kind of overfitting. Okay. So how can you determine whether a model is overfitting? It needs to be determined based on both of the training error and test error. Okay. So overfitting is say like a model is too complicated, so you have too many nodes. Okay. And training error is small. That means you fit well into the training data set, but test error is large. That means it cannot be generalized. But there's another term called underfitting, which indicate the model is too simple. Both training and test error are large. For example, you pick a tree with just one node here, then its training and test error, they are still close, but their magnitude is big. Okay, this is called kind of underfitting. That means you didn't train your model well. Then what will be the solution of prevent overfitting? There's one very intuitive, very easy solution is you increase the size of the training data. Give more information for training the model can help with reduce the difference between training and test error. Make the model to general enough. Okay. So here is an example that we say we increase the size of training data. So this is the original population of data, and giving more, then we'll find out the gap will be reduced. Okay. We'll reduce the difference. But if we have limited training data, then what should we do? We need to control the model complexity. Okay. First, we need to select the model. Check whether the model is accurate enough or if the model is easy to overfit. So this model selection typically performed during the model building. Okay. And also, such kind of model selection is utilized to ensure that model is not overly complex to avoid overfitting. And such kind of selection usually needs generalization error, but sometimes we can also use validation data set. So how can we get validation data set? The validation data set is usually a chunk in the training data set. That means we split the training data set further to two parts. One is still training, another is validation. Okay. So the good thing is you have more confidence on the generalizability of your model. But the drawback is actually you use less data for training. That means your model might not be in a good enough structure. And for a decision tree, select a different model of decision tree. That means select different tree structure. But such kind of selection can also be done with organizing the tree structure. That means first is called pre-pruning. Okay. That means we grow a tree and to some level, then we say, okay, good enough. I stop here. Okay, I stop here. This is called pre-pruning. We didn't grow the tree to its ultimate scale, to its largest scale. We stop early when it grows to some level. So this pre-pruning can be realized by first stop the algorithm before it becomes a fully grown tree. And such kind of stopping criteria for a node is typically composed of two parts. One is we stop if all instances belong to the same class. That means the node becomes pure enough. It is not necessary to further grow the node. Okay. And stop if all the attribute value are the same. Okay. And we can have more restrictive conditions. We stop if the number of instances is less than some user-specified threshold. That means you have very real samples to check the impurity of the node. For example, the number of instances contained in this node is just 1 or 2. Then that is not representative enough. Then this node becomes unnecessary, okay, meaningless, too specific. You don't have sufficient data to verify your hypothesis made on this node. And stop if class distribution of instances are independent of the available features. That means the data points distribution have no relationship with the inputs. That means you don't have further criteria to judge. Then why don't you stop? And further growing means nothing. And stop if expanding the current node does not improve impurity measure. This is very intuitive. That means you further split, they are still ambiguous. You further split, they are still ambiguous. Then the ambiguity is not improved or solved by further growing the tree. Then you directly drop this part because those structures are meaningless. And stop if estimated generalization error falls below certain threshold. That means you further grow the tree, it cannot be further generalized, then you stop. Okay. And another strategy is called post pruning. That means you grow the tree to whatever possible scale it will be, then you decide to cut its structure. And one strategy is called subtree replacement. That means you have a very complicated tree. Okay. Subtree replacement means you replace this whole structure. So you will trim the nodes, that means cut the nodes of the decision tree in a bottom-up fashion. Okay. And if the generalization error improves after trimming, then replace subtree with a leaf node. So if you cut this part of subtree and replace it with a node, then you find out the generalization error drops, that means improves. Then you just replace it. Okay. That means this part of specific tree does not help the model performance. Or the class label of leaf node is determined from the majority class of instances in the subtree. So if you use all the instances contained in the node of the subtree together, integrate them together, or aggregate them together into one node. Okay, then you do the decision making based on all the instances here after you replacing the subtree with a leaf node. Okay. Another is called subtree raising. This is very tricky. It's not frequently used, but sometimes can help. It is like in a in your application, sometimes you find out a tree structure, subtree structure is very useful. For example, this structure is very useful. Then you find another model. Okay, you find this is a weird structure, and you directly replace it with this one. Okay. Then you expect that it can help. Well, sometimes it do, sometimes it does, but sometimes it doesn't. Okay. It's just some empirical trial based on experience. So one very important model evaluation, the purpose is we want to estimate the performance of our model on some unseen data. Usually it's test data. So in evaluating your developed data-driven models, we don't look at training error, we don't look at validation error. We only look at test error. Okay. Test error, we trust it is a kind of trustable performance. It is performance based on some unseen data, which means something more important. Okay. And to do such kind of evaluation, you can do reserve K% for training and the remaining 100 minus K% for testing. Usually is 70% training, 30% testing. Or you can do random subsampling, and which is kind of repeated out. You're using random sampling to generate kind of 70% data in training and 30% in testing with via random sampling. Okay. There's a special case if you have a very limited data points, for example, 100 data points, you want to develop a machine learning model. Usually it is very challenging. Okay, 100 data carries very limited information. And there's a strategy that you have to adopt, which is called cross-validation. Try the best to fully utilize information contained in these limited data points. And this so-called cross-validation idea is very simple. You have a data set. You can cut it with average amount to some of the chunks. Okay, they're disjoint subsets. And here is three chunks. Then you repeat, you cut it to how many partitions, then you repeat it how many times, okay? So here is 3 partitions, then you repeat 3 times. The first, you pick first 2 as the training and last one as the testing. The second is you pick the first and last chunk as training and the middle one as testing. And the last trial, the last 2 as training and the first one as testing, okay? So it's kind of, this is called K-fold cross-validation. And this is the last choice that you would like to try if you have very limited data points. Okay. And the K-fold cross-validation results, usually we don't trust. But if you don't have sufficient samples to further show the performance of the model, you have to go with it. And this is sometimes we call 无奈之举, okay? So you have to go with the K-fold cross-validation. And there's some even more extreme strategy, which is called leave one out. That means you have 100 data points, you use 99 to do the training, and the last one to do the testing. Okay. And this is very extreme case. In the past, people might accept and regard it as a preliminary results, but at the current age, usually people won't buy it. Okay, leave one out is too extreme, this case. But sometimes you don't have choice. For example, you want to build up a model to predicting the failure of a nuclear power plant. Look at the back 100 years. How many failure of nuclear power plant you can collect? How many? Very few. You can count with your hands. Otherwise, the earth is destroyed. Okay, we are all gone, right? So this is called kind of real case example. So you won't have much examples in this kind of application scenario. So in this limited sample, you have to go with it. So this kind of threefold cross-validation illustration of the threefold cross-validation. I've talked about this. I go with just skip these slides. There are two types of cross-validation. One is directly to do a repeated cross-validation. Another is called stratified cross-validation. The only difference is that in a stratified cross-validation, it usually happens in the classification problem. In a classification problem, sometimes you will have data that class 1, which is smaller than class 2, okay? The class 2 has a small area. Probably here, I didn't draw it well. Let me draw some more extreme case. So in a data set, most of they are class 1 and remaining class 2. Okay. Then in tenfold cross-validation, you cut them to tenfold. If each fold, they might also be kind of like this. Okay, each fold. They will also be like this, C1 and C2. This is not good because even every fold you have imbalanced data. So people will think about it. Okay, I do data balancing in each of the folds. So I just generate each fold based on the amount of real examples. I sample the same amount from the abundant examples to build up a kind of fair fold to do the model training, then the remaining to do a classification. Based on this strategy, we expect that the derived model can be more useful. Okay. You can also like use nested cross-validation approach for model selection and evaluation. Okay. Nested means first we use the full data and next we use a smaller amount, okay, to gradually check its generalizability. Okay, so we'll finish these slides, then we go to the next one. We talk about some regression. Regression contents. But before I talk about regression contents, I would like to mention one thing. So can you guys online see my web browser? Huh? Can you guys see my, no? Oh yes, cannot? Let me. Yeah, for this one. Right now you guys can see, right? Yeah, our school. So this is another context besides the Big Bay Area policy data contest I introduced in the previous announcement. This is a global AI challenge organized by Hong Kong EMSD. This contest actually do one task, which is the which is the cooling demand prediction. Yeah, the building cooling demand prediction. Okay, so this is the test. This is the forecasting problem. Basically, the EMSD will provide data, and you guys using those data to do the cooling load forecasting. It's a regression problem. So our school is recruiting students to join this contest. I don't know whether you guys received an email kind of couple of weeks ago. So each team can also apply for the sponsor grants about 35K Hong Kong dollars if you find out a supervisor. So I'm encourage you guys to form team if you don't have a good topic of the project, or if you want to take a more challenging project, and I will be the supervisor. Okay, so I can give you advices how to do it. And yeah, so basically that's the background. So I encourage you guys good at coding and good at regression tasks, or especially you guys who know XGBoost well, or some other regression methods, please contact me, okay? So you guys can form team and also apply for the financial support from the school in joining this contest. The deadline is soon, remember, I remember. The deadline is the end of this month, probably next week, yeah? So it's called Global AI Challenge for Building ENM Facilities, okay? 10 days, see, 10 days. Oh, really? Well, the price is big. It's 200K US dollars. I hope it's not Hong Kong dollars, okay? Yeah, so the benefits is very attractive. You can, I didn't share, sorry. Yeah, the price they said is 200K, but I guess this 200K will be divided into like the first winner, second winner, and third winner, okay? But the school will also provide financial support if you can find the faculty in a school to supervise your performance, to supervise your project, okay? So you guys can form multiple teams, or one team. I can supervise multiple teams. So if you like, let me see the prices. Most efficient algorithms. And oh, they have different category of awards. Okay, so this 200K, yeah, 200K US dollars will be divided into different chunks. Okay, you might win kind of most innovative use of data award, most innovative AI solution award, and so kind of. And it will be gold awards, silver award, bronze awards, according to your score in Part B. What is the Part B? Part B probably just the road forecasting competition, okay? All right. So later I will also organize an announcement to all of you. I think it's a good experience. It's also good for career development if you can win an award or becoming some top perform teams. And that will be a very promising proof of your capability in AI area when you apply for your jobs, okay? And now I'm going to talk about regression, okay? So given a collection, the regression compared with the classification is given a collection of records, the input training data. The data is also organized as a tuple where the X as the input and Y is the target. The difference compared with the classification problem is here, the Y is a numerical. For example, in the context, Y will be the cooling load of the building, and X will be a lot of inputs, a lot of building attributes related to the cooling load demand, okay? So what you want to do is you want to learn a model structure which predicts the value of Y based on the value of X. So I guess everyone knows linear regression, right? I hope here we all know linear regression. So linear regression has a very basic regression form. It is composed of two terms. The first term is a intercept, and the second term is a linear coefficient multiplied with each of the input attributes, p dimension from 1 to p, okay? P dimensional inputs, and xj, j equal to 1 to p means each of the dimension, okay? So the learning goal is to minimal the residual between the predicted Y and the observed Y. The F, XB, X and beta with X and beta is this one. This one is a Y hat, okay? This form outputs the estimated value of Y based on the value of X. And fitting a linear model is to estimate the beta 0 and the beta j, given the value of observed Y and observed X. We want to minimize their residuals. We optimize beta. How many ways to do the linear regression? If you took undergraduate statistical course, you will know maximum likelihood estimation, okay, MLE. Basically, you assume beta follows a Gaussian. And based on the Gaussian form, you estimate the likelihood of the beta. And you set the beta to a value with the maximum likelihood, okay? So MLE. The second one is if you are from the optimization aspect, you will know the least square feet. Square feet, okay. And the third is called Bayesian inference. Bayesian inference idea close to MLE, okay. And if you are a machine learning guy, that must be gradient descent, okay. So these are the four strategies to do linear regression for fitting the linear model, a linear regression model. So nowadays, people are all GD, gradient descent, okay. And I would like to introduce an interesting variant of linear regression, which is called ridge. Nothing different, but we have an additional term, penalty term, lambda multiply the summation of the beta j square. So what does this mean? So this one is a Y hat, okay. So we want to penalize the beta j, which contribute less into estimating of the into the fitting of the linear model. And such kind of penalty can be done if the beta cancel out due to a collinearity, okay. So this penalty is to penalize, to deal with the in general or most high level, the ridge regression, to deal with the collinearity issue. Yeah. Using mouse to write is very difficult. Can I type? Oh, yeah. Collinearity. New word. I need to thank Kayan. Thank you for your suggestion. I found out there's a text option. I have never used this option. I'm so stupid. Okay. Then what is a lasso? Lasso have also an extra term, but penalize the absolute value of beta. The big difference is lasso can penalize beta to 0, but reach can only penalize beta infinitely approaching 0. Okay. So lasso can select variables or select features, but reach cannot. Because reach still leave some of the value for each of the coefficient. It does not directly return. You still need to judge by yourself. Okay. Then this is a very classical figure. What does this figure mean? This is this shape describes the area of the penalty. It's because beta, absolute value of beta. So it will become like this. This is beta square. So it looks like this. Okay. This is the contour of the response of the lasso regression. And this point means the minimum of the beta, the best estimate of the beta. And this is reach. Okay. And the interesting part is the contour of lasso move pivots according to setting beta equal to 0. So you can touch this point that beta penalize beta exactly equal to 0. Okay. But reach cannot. When reach touch this point, and this is the beta very close to 0, but not equal to 0. Okay. So this is the illustration of this figure. All right. So this is a reach lasso. We finished the linear regression models very quick. I guess most of you have know that. So I just recap. And next, I would like to talk about the k-nearest neighbor regression. K-nearest neighbor regression is similar to the k-means. It's similar to the k-nearest neighbor classification. Logic is the same. First, you need to find out its neighbors. This is a set of neighbors, and every x belongs to the neighbors we will select. And for each of the x we select, it has an associated y. And the estimation is just an average of this y. Okay? We take an average of this y. That means we take the average of y of the neighbor. Then regression tree. Regression tree is also similar to classification tree, but the mechanism of estimating y is a little bit different. It fits a piecewise linear, okay, a piecewise constant. So first, according to the tree structure, given a new data, you will find out which region that the data belongs to. And for each of the region, you have fitting a CM, which is all the y of the axis you observed in a region. CM is equal to the average of y condition on all the x belongs to that region. Okay. I probably have a slide later. Yeah, it's here. Yeah. So growing of a regression tree is a greedy process, or they use a greedy split strategy. What does that mean? So split of the trees to do the regression relies on first finding out the point to do the split. Okay. Because the inputs are now not categorical, they are numerical. So to split attributes with a numerical value, we need to find out the point to make it as two parts. So xj less than or equal to s will becomes one direction. Okay. So if xj less than s, we go this way. If xj larger than s, we go another way. Okay. And how to determine the s? And how to determine the j? Which parameter we need to select to split? And it is a two-layer minimization problem. First, we minimize the overall performance with determining j and s. Next, based on each of the j and s, we do minimize the c. Okay, so we minimize the c so that the residual between y and c, they are close. Okay, so in a regression tree, its output usually is constants. It's constants, and so constants. It's kind of like this. If you have a data fluctuating like this, it will return quite a number of constants for you. Okay, this is because it naturally have such kind of prediction strategy. All right. Okay, I will stop here and take a break. Let's come back at 9:10. Then we will go through the SVM regression and also the neural network concepts. Yeah, neural network concepts. Majorly, we will talk about the neural network, the gradient descent and back propagation. Okay.那个是好像是你是来自 policy， 但是你们学院 promote 到的对吧？就是你们学院的老师想组织一个这样，应该是小组的，然后要发邮件给你们那个老师叫。哦，那他这个比赛组织的可不可以？感觉好像好像带的啊，也没有网站。我看当时我看也疯了，他给我发了一个 poster， 然后居然没有报名的信息，我当时被你们的邮件问懵了。对，今天这个比赛是香港电机电。这样直接调出来。我还没对，因为疫情还没见过。是哪呢？我还以为是个女生，我还没见过你们的体内，他从来没跟我线上见过。我们从来都是用 email 交流的。哦。 是 M1 的芯片，那就很大。对，如果你不是 Intel 的芯片，你不想用 Web 的话，可以的，就这样 Web 卡。这样因为这种是免费的软件，它不能帮你搞非常好的兼容性，兼容性几乎不能用。对，它用 Mac 系统。我本来是意思说，你们可以编程的话，用这个就可以。如果不行的话，你们有没有什么关系？就是 SDSS。学校好像是有 SDSS， 但 SDSS 的话，差不多是有界面。啊？
它是什么破解版？那不是也是枪版吗？
破解版的 SDSS。那你们如果能下到破解版，那也可以，因为学校应该我记得是每个人都有个 license， 有个开课生。可以跟开上去，它是有 API 的，但它自己也有自带的那个方式，点发，只要你拖几个那个图案上，它就可以，它那个一个墙一个墙一个是那个，还有什么上，然后拉一些链子，就然后点一个 run。SDSS 是不行操作的，就是它不操作。哦。对。你不需要知道它背后的逻辑，你只要知道它到底是用来做分类还是用来做回归的。当然你比较一下，因为你也不知道这个回归方法针对你的对象在哪一个地方，所以你都得试。全部都得试，你没有一开始就会知道，所以这叫非常 mining， 就是什么叫 mining？ 你挖矿，你就得不停的试，能挖到就行，你 mining 出来，没挖不到呢。对啊，你们破解应该是你们有一个 data set 和一个 problem， 然后最后你要告诉我哪一个算法会解决这个问题，就它的结果是什么。然后你们还对，你们还有考试，考试应该蛮简单，就是课件里面。不是问答。
问答就是要
选择题、问答题，一点点题法。
问答题
就是你们文学类的，就是给一个问题写它，就是给一个他们定义的理解。
定义的理解。
或者给你们一个场景，你们说大概怎么样会有什么样的结果？现在好像不能，因为它变成要 on campus。before 设定是考试和校园，这在校内考。
线下的。
但是我们的课是 online 的，好像online 的话，那就多关注。online 的话，我 online 考试都是为了帮助大家能，对啊，所以也不至于说要怎么样的。
不是我们的，是我们的问题，不是我们。
我讲的很清楚。对，我看手不行。
不是我背哪种是什么药啊？不是我，你的英语都不能，你这就是这样一个形象，这不太是表面的，然后这是药治疗的，对这种药单塞的。哇，这么你们不是气候的消息吗？什么？
麻烦你。
Okay, let's continue. The SVM regression. SVM regression is also very similar to SVM classification, but if you want to change the function of classification to regression, you have to modify something here. That's the constraints are modified. It is no longer y multiply. So if you see that a lot of machine learning tasks, they say y, I need to use text. Otherwise, Cayenne will say it is difficult to see. Okay. Yeah. So for classification, usually people will use such kind of x multiplied beta plus b. Okay. Using this form, but regression in SVM, you see the difference is y minus x multiply beta plus b. What is the difference? If you go back to our linear regression concepts, you will see that this is a residual. X multiplied beta plus b is a linear regression form, and that's the estimated y. And you have observed y, and less than equal to the error specified in SVM. That means based on such kind of regression, we expect the SVM can return a performance which is at least this error level. Okay. Not much to say about SVM regression, just a little bit very extending the constraints in a support vector machine. It's here. The only difference is here. You still need to find maximize the margin, but subject to a different constraint to have all residuals less than. You want to develop a linear form to have all residual less than this. Okay. But this is a very ideal case. In the real case, you probably also need to tolerate some of the extreme case. Otherwise, you cannot find out a good decision boundary, a good manifold. So you can see here, we can also in SVM regression, we can also introduce a slack variable epsilon to tolerate some of the extreme case that your error cannot be less than the preset error level. Okay. But and also definitely you can use the kernel trick. You can project X to another space, then fit as a linear form. That means you have text y minus kernel of X multiply beta plus b. Okay, so the kernel trick always first projecting X to a hyperplane, then fit it as a linear regression. So we finish all the simple contents, then we go to the fundamental of the deep learning, which is nowadays deep learning is most of the deep learning rely on neural network structure. Then we will start very simple case, an artificial neural network. Okay, start with the shallow neural network. So neural network like KNN, K nearest neighbor, and support vector machine, they both have classification and regression versions. Okay, so that means the algorithm can both do classification and regression. So that's using some classification as an example. Given a data set with 3 dimensions of X and a response Y. Y is a binary class. So a neural network is like taking the inputs with a number of neurons, then the output as 1 neuron, then you are going to build up a complicated black box network structure to make sure that you are able to do classification of Y based on the input of the X. So this is a very simple neural network example. It just has 2 layers, input layer and output layer. Okay, it even does not have any hidden layer. Okay. So each input nodes in a neural network indicates a dimension of attributes in the input. What does the dimension of attributes? X1 is 1 dimension. Then it will occupy 1 input node. X2 is another dimension. It will occupy another input node. X3 is the 3rd dimension, and it will occupy another input node. How many of the outputs you are concerned? The output is 1 dimension. So you have 1 output node here. Okay. Here we adopt a very simple structure. You can make it more complicated, but here we use a very simple structure. The input node directly linked to the output nodes with a weight 0.3. So the weight means the strength of the information will pass from the input node to another node. Or mathematically, it just indicates weighted average. Okay, so 3 links, that means 3 weights. So it's 0.3 multiply x1, 0.3 multiply x2, 0.3 multiply x3, and add them together. So sometimes it's called summation of the weights multiplied with x. So this is based on the number, okay? Wi, xi. And in linear algebra, we will write vector of w multiply a vector of x. Okay. So this is a linear algebra presentation. So if you read papers, you can see 2 different expressions. They actually describe the same thing. There's a bias term here, t equal to 0.4. So this one is a kind of wx minus b. See, this is a linear regression part. And the difference is you have an activation function, okay, to do a transformation of this linear regression output. And here we use a sine function, which means if x results, if this input is larger than or equal to 0, then we classify as +1. If this component is less than 0, then we classify y as -1. Okay, good to understand, clear, right? So we can see that the model is an assembling of interconnected nodes and weighted links. This is a presentation from a graphical perspective. Mathematically, it indicates a weighted average of information from different nodes and outputs that kind of average to another node. So output node sums up each of input value according to the weights of its links, its weighted average, and compare output node against the sum of the threshold. This is for classification, okay? So this is a simple perceptron model, 2 layers, 1 input layer and 1 output layer, or sometimes we call single layer perceptron. And the usual ANN, artificial neural networks we refer to, is a network of such kind of structure. 1 input layer, 1 hidden layer, and 1 output layer, 3 layers. So sometimes we call it 3-layer perceptron. 3-layer perceptron. Three-layer perceptron. Okay. Includes input layer, hidden layer, and output layer. And you might question, you will ask, hello, professor, how can we determine the size of the input layer, the size of the hidden layer, and the size of the output layer? What does the size mean? In input layer, the size means the number of input nodes. Where should I put? I put it here. Okay, so input layer size. So layer size means number of nodes in the layer. So the interesting thing is, in the input layer, the number of the input nodes will always be equal to the dimension of the input space, or simply says the number of attributes you will fit into the neural network. So here, your data only have 5 attributes, x1 to x5, then the input nodes will be 5. Okay, the nodes in the input layer will be 5. Output layer size is determined based on the same way. How many outputs you are going to model in your problem. Here, you just have one Y. You do regression for 1Y or do classification for 1Y, then the output node is 1. If you have 2 Ys, that means Y1 and Y2 you need to estimate, then that means number of output nodes will be 2. The tricky part is the number of hidden nodes. This needs to be pre-specified because gradient descent cannot help you to determine the number of hidden nodes. Gradient descent help you to estimate W and B, the bias. This one, in a lot of times, you set a number of values. Trial and error. It's kind of trial and error process. Basically, sometimes people do training or a 3-layer perceptron. They give 100 choices of number of hidden layers. That means train 100 neural networks and select the best one. Okay, select the best one. Then the number of hidden layer will be set to that one. Okay. And then let's look at the meaning of each neuron. Each neuron has following components. First, it has a receiving side. This receiving side take the weighted average of the input. For example, this WI summation from little I equal to 1 to 3 as SI, okay? And then the SI will be fit into an activation function G. And this activation function have different choices. In a 3-layer perceptron, it mostly utilizes sigmoid. Or sometimes has hypertangent or exponential or identity. So you have different activation function can use. So you randomly choose one of them, but most of the time people choose sigmoid. Okay. But in deep learning, the activation function of sigmoid does not fit well. Okay. So in deep learning, most of the activation function is called ReLU or leaky ReLU nowadays. Okay. And the third component is the output side. That means you take the value from this GSI and as the output to pass the information to the next node. So you can see here, we have a 3-stage calculation. First is summation weighted average of W multiply I and put it into an activation function and equal to an output passed to another node, okay? So various types of neural network topology, I have talked a single layer and multi-layer. So the number of layers can be set by you, very arbitrary. You want it to be 3-layer, then it will be 3-layer. You just want to try a single layer, then a single layer. Nowadays, the way of determining the optimal layer number of layers for a neural network, there's no such kind of science. Okay, it's all training and determining based on your experience, based on your experiments. Or you can use some heuristic methods to determine, but that's not the optimal, global optimal, it's local optimal. That's another story. It's a kind of architecture optimization. So to develop a neural network model, you need to do a number of things. You need to determine number of layers. You usually do trial and error or heuristic, because deciding number of layers is kind of NP hard. Number of nodes in layers. The input and output layer, you know. Hidden layer. The number of nodes in the hidden layers is the most tricky one. The gradient descent. Yeah, and choice of activation function. So you can see compare with other like linear regression, SVM regression tree, the neural network model development is the most troubleful one because you have so many hyperparameters, needs your experimental trials, the number of layers, the number of nodes, the choice of activation functions. They are all there's no algorithm to automatically determine the optimal ones for you. Okay. So one good practice people have tried before is we develop, for example, 10,000 network structures and select the best one out of them or best 5 out of them. All right. So the gradient descent only utilized to determine WMB, the weights and bias. So this WMB scale will be determined once you have specified the number of layers, number of nodes in the layers, and your choice of activation function. Okay. Once those determined, that means the architecture of the network or the topology of the network determined, then next you apply the gradient descent. Okay. So the gradient descent cannot help you to determine those hyperparameters. So here we talk about the various type of activation functions. I have shared some of them previously. And linear, sigmoid, hypertangent. Okay, sometimes we can do sine, but not really. So this slide is just an illustrative example, show you the single layer perceptron calculation. In the previous slides, here, a single layer. So it contains only input and output node and one activation function as sine at the end. So you input, you know the links and the bias. Here you assume to, you have been assumed that you know the weights and bias. Usually this 0.3, 0.3, 0.3, and 0.4 needs to be estimated based on data. Then given a new data, you can base on this network to do a calculation. First 101, you input x1, x2, x3 with 101. Then you get it's 0.6 minus 0.4, then it's equal to 0.2. Then you put it into the sine function. And you see that it is larger than or equal to 0. So you give a y positive 1 label. And this is the procedure of using single layer network to do classification. And the key issue I've said, like once you fix the topology, and what you need to learn is those weights. And this weight 0 is usually the bias, okay? So to update those weights, you use a gradient descent. This lambda is the learning rate. This y minus the estimate multiply x is the gradient, okay? Gradient. Let me erase it. Let me use text. Gradient, grade, okay? So you continuously run such kind of updating procedure until the stopping condition is met. That means the algorithm is converged. So the weights cannot be further updated or the weights cannot be further modified. Then that means that the structure of the network becomes stable, becomes converged, okay? So this is a weight form updating formula. The intuition is to do updating weight based on the error term. The feedback is a kind of feedback control. So sometimes control people also study kind of network from the control perspective. So if gradient equals 0, you don't need to do any update. So in deep learning, we will usually face a situation that all the gradient, a high dimension of gradient equals 0, and that is called saddle point because you don't have direction to go up or go down, okay? And E equal to 2, that means weight must be increased so that the objective function can be increased. then E equal to -2, then that means weight must be decreased so that objective function can be further decreased. Okay. And this is the example of iteratively computing. Okay. So you can see the epoch means the updating of the weights for the epoch 5 and epoch 6. They are going to converge. The weights is no longer changed. Okay. And this 0 to 8 means the weights computed by fitting data points from 0 to 8. So you see, for each epoch, you are going to feed data from 0 to 8 into the network to computing the weights. At the beginning, it's initialized as 0, okay? But by feeding one data, then it becomes this, and later, okay? Then each epoch is after filling all the data points, finish all the updating, then you go to next repeating. All right, I would like to stop here. So the latter slides talking about more details of the gradient descent and the backpropagation for ANN. We will discuss in next class. I think today is good enough. Some of you already feel very sleepy. Okay. So we stop here, and I will see you guys next week. Bye-bye. Have a nice night. Have a nice evening.